Hey everyone, welcome back. So today we're going to be talking about another interesting problem. We're going to be building LRU cache from scratch. We're going to be defining functional and non-functional requirements, and we're going to be making sure that we satisfy each of these requirements while building the LRU cache. Before we get started, let's try to understand what cache actually is, right? Cache is a mechanism where the data that you store it in memory as well, which is your RAM. The reason you're doing that is when you want to fetch a frequently accessed data, you don't want to go all the way back to your database, which is ideally stored in a hard disk, fetch that value and return, right? If you have stored it in memory or in a cache, uh, you can easily fetch the data, and the access time to fetch the data is very fast compared to going and fetching it from a hard disk. A lot of services provide cache. One of the famous services is Redis. And talking about what LRU is, LRU stands for least recently used, and I'm pretty sure that it's one of the most commonly used terms. What is LRU, and what does it tell you? What does LRU actually mean, right? So in a cache, right, you have a diff like for example, let us say that you store in a cache, you store data in form of key and value, right? But when you're storing a data in memory, your RAM also has some certain capacity, right, that it can hold. And you're only trying to store frequently accessed items in your cache, right? So when that particular capacity exceeds a certain limit, right, you want to evict the data from your cache. Right? Why do you want to evict it? You can evict it so that you can add newer items to the cache, right? Now, there are different mechanisms on how you can evict your data from the cache. It can be your TTL, which is time to live, or it can be your least frequently used. It can be least recently used, right? So these are different eviction strategies that you can use to evict the data from your cache so that it has enough storage for you to add new elements, right? So, but like I told you that cache is something which holds the frequently accessed element. We need to be very careful about what we're trying to remove, right? Because if we are removing a frequently accessed element in a cache, let's say through TTL, that is still going to cause us a problem. Why? Because if you have to fetch the data for it again and it's not present in the cache, you have to back to the database, fetch it, store it in the cache, and then return it, right? So you have to be very careful about what you're trying to evict and how you're going to evict. On what strategy are you going to evict? So what does LRU tell you? LRU LRU ideally tells you that in the cache, whatever data is least recently used, evict it. Right? It's as simple as it is. Whatever is least recently used, evict it. Whatever is most recently used, keep it. Right? That's all LRU says. Right? So with that understanding, let's define our requirements and uh, let's get started on that. Okay. So let's first talk about the functional requirements. So ideally, I'm going to be talking about non-functional requirements as well when I'm defining functional requirements. You'll see. Our first requirement is that you want to be able to put and get the value from the cache, right? This is going to be a key value based cache, right? So you'd want to be able to add a value and remove a value from the cache, right? So the first requirement is put of key comma value should add the data to cache, right? Now, like I told you, cache, the reason we're using cache is to make sure that our access times are faster, our read and writes are faster, right? So what should be the time complexity at which we should be able to add a value, right? It should be constant time. So we need to make sure that our particular cache is is able to access data in a constant time, right? So this will be in O of 1, right? Second requirement would be get of key comma value should, sorry, get of key, right? So you need a value for this, right? Should return you the value for that key, right? This also will be of 1, right? The next requirement is the type that we are trying to add to a cache. It can be anything. It can be an integer. It can be a string. It can be anything, right? So we need to make sure that the type of key and value is generic. Type of key and value is generic. Fourth point. When you are trying to access a particular element, right? For example, you're trying to get an element. When you're trying to get an element, you are accessing that element in the cache, right? So that element now becomes your recently used element, right? Similarly, whenever you add a new element to the cache, that becomes your most recently used element, right? So based on the operation, I'm just going to make it generic. Based on the operation, either get or put, the most recently used should be reallocated, right? Fifth point. If in case of put of key comma value, if your key already exists, you're gonna update the value. Okay, if put comma key comma value already exists, update the value, right? Okay, so okay, perfect. Now, what could be another requirement? If get of key does not exist, you can return either null or you can return -1, whatever you want, right? The next point, the cache should have a capacity, right? We can define the capacity, but it should have a certain capacity. The eighth point is if the cache has reached a capacity and you're trying to add a new value, right? Like we already discussed, if the cache has reached its capacity, in that case, you will have to evict the least recently used item before adding that particular value to the cache, right? If cache has reached its capacity, uh, evict the least recently used item, right? Perfect. I think, okay, I think one more major important point that we need to include. This comes in a non-functional requirement. Currently, whatever we're looking at, we only saw it from a single threaded point of view. But in a real system, you're going to have it multi-threaded, right? You're going to have multiple threads trying to access, get, or put a value, right? So these things needs to be handled, right? So thread safety, I'm just going to mention that thread safety might should be ensured. Perfect. So with all our requirements, let's try to get started. Let's try to understand how an LRU cache works. So the first 2 points that we discussed, right, uh, which says that which says that you should be able to put a key value and get a key value in O of 1, right? So it should be of constant time, right? When we say that, what is the first data structure that comes to our mind for us to implement it, right? It's nothing but hash map, right? So the first thing that comes to our mind is we should be using a hash map because get and put values will ensure the time complexity of O of 1, right? So, okay, so then we decide, okay, let's do one thing. Let's go with the hash map. And in the hash map, we are going to simply add the key and the value to it, corresponding value to it. And whenever the key is asked for, we will just return this particular value. Okay, all sorted? No. Why? Because in a hash map, you can definitely add key and value, which is going to be unique and which is going to give you O of 1 complexity. But the issue is that the ordering of the key and value is not determined. It is random in nature, right? But for us to implement an LRU, the ordering of the element is paramount, right? We need to make sure that the elements are ordered because we then know where the elements are and how recently or most recently the elements are being used, right? So, okay, then we have to think of something else to fix that particular problem, right? Now, the problem that we have is ordering of the elements, right? Okay, so what are we going to do? We have fixed this problem of returning the value in O of 1, right? Now we have to look at how can we order the elements. Let's think about it. For us to order the elements, we need to ideally put it in a place where we can maintain that order. Right? It can be anything that you can use, but it needs to be something where you know the order at any given time. For example, let us say that you put that particular value in an array, right? You put the value in an array, and in your hash map, you store the location of that particular value, right? You can do that. But again, there's a lot of complexities with that, right? Why? Because whenever you're trying to uh, whenever you're trying to add a new value or remove a value, you're ideally replacing or moving the entire array, right? When you're trying to evict a value, you're removing that part in your array. When you're removing that part, you need to make sure that your uh, array, it needs to shift either towards the left or towards the right, right? So that will give you a complexity of over one, right? So instead, what we can do is we can think about an approach where we store the value, right, somewhere, right? We store the value. Let us say that we store this key and value somewhere, right? And what we're going to do is this particular address, we're going to store it in a hash map, right? So this let's call this a node, right? Let's call this a node. This node is going to have a key and a value, right? And this particular key in your hash map would ideally store the address of this node, right? Now, we've solved one part of the problem where you are trying to add it. Now, what about ordering of it? So we know the address of one node, right? What about so when you want an order for something, right? You need to know what your adjacent elements are, right? Because finding an order is a relative term, right? So you need to know what your adjacent elements are. So for that, what we're going to do is in this particular node, we're also going to store the address of the left node and also the address of the right node, right? So now what's going to happen is if you're trying to add, for example, in your LRU in your cache, you're trying to add, uh, let's say you're trying to add first operation, you're trying to add 1 comma 2. Second operation, this is put, okay? You're trying to add 2 comma 3, 4 comma 5, right? Now what you're going to do is you're going to keep adding 1, 2, 3, sorry, 1, 2, 4, right? And you're going to attach it to its adjacent elements, right? So that your 2 knows what is the element towards its left and also towards its right, right? We need this because this will give us flexibility on how we how we evict or how we remove the nodes or how we add the nodes, right? Now, with what kind of data structures can this be achieved, right? This is called as doubly linked list, right? Why doubly? Because linked list you are only pointing forward. Here you're pointing backward as well, right? That's why it's called as doubly linked list. So you might have a question. You can be like, "Hey Siddharth, why can't we use just a linked list, right?" Again, the same problem, right? Linked list only moves forward, right? But let us say that we want to evict an element in between, right? So for example, if you're using only linked list, right? So you're using 1, 2, and 4. So if you want to evict 2 from your LRU cache for some reason, you'll have to connect 1 with 4, right? Since you're only moving forward, you know what the next element is, but you don't know what your previous element is, right? So this is why you cannot use a linked list, right? Perfect. So that being said, we're going to need two things. One is your hash map, which would ideally have the capacity, which would have the key, which would have the node address. Right. Perfect. And the next one is your doubly linked list, which would have the functionalities of adding, removing, all of that, right? We will come to that. So you need another this thing called uh, double linked list. So these two are the data structures that we need, right? So we try to solve leak code problems so many times. We have used doubly linked list, and I'm pretty sure you used hash map as well, right? But the whole point is how we can use it to build a real life application, how we can use it to solve a problem in real time, right? That is the whole point on why we are learning data structure and algorithm, right? Perfect. Now, uh, let us start drawing the classes, and let's define the classes, and let's draw the diagram for it, and let's have the entities and the function that is needed in that. So the first class we would need is a node class, right? A node class. Okay, let me actually do one thing. Let me actually show it you while I'm implementing it so that it would be much faster and much easier to understand. Okay. So what is the first class we need? The first class we need is a node class. Like I told you, so we have defined our node class, right? Now, like I told you that the type of key and value should be generic. We have to keep it generic. So let's just do one thing. Let's keep it as k and v, right? Key and value, right? So we're gonna call it key and v value, right? What else do we need? We need the address of the previous node, right? kv, the left node. Similarly, node k comma v needed for the right node, right? And we need a constructor. So we're going to generate a constructor which includes all this value. Okay? As simple as it is, right? Okay. What is the next class we need, right? So the next one is what? It's a doubly linked list, right? We are building it from scratch, right? So we are building a doubly linked list also from scratch. So we'll be using a doubly linked list. Doubly linked list, right? Over here, what is the what is the parameters that you need for a doubly linked list? So for doubly linked list, we would need the okay. So we have a doubly linked list, right? Now you need to add your key and value, right? Ideally, you need to add your key, sorry, not the value, your key and the address of the left and right node, whatever, right? So you will have a new key in this box. You'll have a new key. You'll have a new key over here. You'll have a new key over here, right? So these two are connected. These two are connected, right? Now, if I have to remove this node and move it over here, right? What would this be connected to? You getting my point? This connection would remain open, right? So we don't want that. So simply what we're going to do to solve that problem is we're going to keep two nodes. We're going to call it first and last node. These two are nothing but dummy nodes, right? So ideally, this would refine our structure and keep it more defined, right? So this is our first node and this is our last node, right? This two is never going to change. Whatever is in between is what we are going to add and remove, right? Okay. So with that, we are going to create a new this thing. So we're going to call it node of key comma v. Actually, I don't need to do it, right? I'm going to call it first node equals to new node of it can be 0 0 and left would be null. For now left is null and right is null, right? Similarly, node of last node, new node of it, it will be 0 0, left would be null and right would be null, right? Now we have created that. What else do we need? Uh, I think we're good, right? If we need anything, we'll add it. So we will generate a constructor. We will simply take these two, right? Okay. So do you need to pass these two? Not required, right? Because this is something that we are setting, right? So here also we don't need to do this. So what we're simply going to do is we're simply going to set it, right? So first node dot right node will be your left node. Uh, sorry, last node, right? Similarly, last node dot left node will be your right node. First node, sorry, first node. So we made that connection, right? Let me show it to you. So your first node and then your last node. First node, last node. First node, first node dot right is your last node. Last node dot left is your first node. Right. So you're done. Okay. Now, what are the methods that we need? Right. So ideally, the data that you have, you'll be adding it to your W linked list. After you added your hash map, you'll need to add that particular key in your W linked list, right? So the first method that we need would be your add method, right? So we're gonna keep it void and we're gonna call it add and whatever node that we want. Node of new node. I'm gonna call it new node. Perfect. Again, similarly to add, we need to get it as well. So public void get of key, right? Okay. So let us actually think, do we need get? We do need it, but probably we don't have to add it over here. Right? I'll come to that, but for now, let's not add it over here. Right? Okay. Now, what is the next thing that we need? In a doubly linked list, right? For example, let us say that you have values like 1, right? You have values like 1, 2, 3, and 4. These are your keys, right? These are your nodes in a doubly linked list. These arrows represent forward and backward, okay? Now, let us say that you are trying to add a value, right? You're trying to add one. Sorry, you're trying to add a new value. For example, 5. The value that you want to add, by value, I mean a key, right? Not the value, key. The key that you want to add is 5. Okay. In a LRU cache, where would you add this particular key? Would you add it in the start or would you add it in the end? We will be adding this value in the start. Right? The reason we are doing that is the most recently used elements would be in the start and the least recently elements would be in the end, right? So you're going to be adding 5 over here. So you're going to connect first to this and last will be over here. Now, if you're trying to get a value, for example, you're trying to get 2, you're trying to get 2, right? What do is you get this value, you return this value, okay? After you return this particular keys value, you will have, so when you access this recently, right? So this one becomes your least recently used now. So what do you have to do? You have to take it, you have to push it to the front. Got it? So why? Because 2 becomes your least recently used element. Sorry, your most recently used element. So that needs to be at the forward, right? And the least recently used element should be always at the end, right? Now you want to evict something, right? When you want to evict the least recently used element, you directly evict 4. Why? Because it is the least recently used element, right? And when you reach the capacity is when you evict it. So let us say that the capacity has been reached. You simply evict this last element and you connect these two elements, right? Now, Uh, yeah, I think it's clear. Let's try to implement it and then we'll take it forward. Right. So your add node is done, right? So now you will have uh, something called public void evict, right? Evict will simply evict the data, right? Now, evict will always evict the data from the last one, right? But like I told you, if you want to access a particular element too, you get it. By get it, what are you doing? You remove this node from this location. So you ideally connect these two. That is what you mean by removing it, right? After you remove it, you have to add it to the first element next to the first node, right? So this we will call it reallocate, right? Public void reallocate of a node, right? So this will be of a node, and what we're going to do is we are going to remove that node and we're going to add it in the front, right? So we'll have another function. Evict is always to evict from the last, right? So we'll have another function public void remove of a node. Observe that evict does not need a parameter because we're removing the last element always. But for remove, you need to know which element you're trying to remove. So what will reallocate do? Reallocate will first call remove, then it will call add. As simple as it is. Right? Perfect. That is it, right. Now, this is our doubly linked list. Now, tell me something. Should our hash map exist in doubly linked list class or should it exist in the LRU class? Does it belong to the doubly linked list class? No, right? Why? Because doubly linked list, the only thing that it's supposed to do, only thing that it's doing is have the nodes, arrange it in the order, remove the node, add the node. That is all. It doesn't care about what the capacity is. It doesn't care about what elements are there, what values are there, nothing, right? It only cares about the linked list, right? So we're going to create another one, which is our LRU cache, the main class. And in this particular class, we are going to, uh, you know, add everything that we need, right? The first thing that we need is our doubly linked list. So we're gonna create a doubly linked list. I'm gonna call it DDL, right? One thing is the access modifier is private, public. I'm assuming that you know it, but if you don't know, you can keep this all these things as private and you can keep it as final as well. The reason being that is you don't want anything to change it during the runtime and you don't want anyone to access it as well, right? Similarly over here, right? Right. So now we have our LRU cache, which DDL, and we have a hash map of key comma value. So I'm going to call this reference map equals to new hash map, right? Okay, so I need to define this as well, right? Okay. Okay. Now tell me something. Uh, what would be the value of the hash map? Would it hold the value of the key, or what would it hold? It will hold the node's value, right? That would be the value. So this will also be key, right? Perfect. So we have defined a hash map. Let me not, yeah, let me just name it. Now, what else do you need? You need the capacity, right? Let me give the capacity as integer, right? Perfect. Now, we need a constructor, so I'm gonna add a constructor. So let me add all three. I'm gonna change it, right? So here, if you look at it, doubly linked list, is this something that would be needed to be sent as a para? No, not required. Is hash map needed to be sent as a para? No, we only need the capacity, right? So these two things will not be needed, right? So I can just say this dot ddl equals to new doubly linked list. That's it, right? And capacity of this capacity, and also reference this dot reference map equals to new hash map, right? As simple as it is. Now, what functions will LRE cache have? It will only have the functions that is publicly visible to the user, right? So public void put of the key and the value, right? This is the first one, and the next one would be get, right? For what would be value, right? So get of the key, right? Now I'm gonna return some value for now so that there's no error, right? Return, right? Mm, can I return that? Okay, yeah. Now, one more important thing that I forgot to mention. What about these methods over here? I have named it as public, public, public. What do you think? Should reallocate be public? No, it should be private because no other method should access it. It's internal, right? Should evict be this thing? It can be protected as well, but I'm going to keep it as public. You're going to add that, let that be, let this be private, and you're going to remove, right? This also I want to make it private. Perfect, right? So keep in mind, whatever we're doing it only for single threaded for now, and we will extend it to multi-threaded. Right, we'll come to that, but for now, we're going to keep it as single thread. Now, let us go into the implementation. Right? Let's try to add a node here. So when you want to add a particular node, what did I tell you? I told you that when you want to add a node, you have first, right? Let this be there, and this would have a 5, 6, and last. Right? These are existing this thing. Let us say I'm calling put of 10 comma 12. This is a key and value. Right? So I want to add 10 over here. So what do I have to do? I have to add it to the start. So if you currently see your first and your 5 is linked. So I want to bring 10 in between this. So what do I have to do? I have to connect 5 to 10 and also 10 to first, right? From 5, we can know the first value. Similarly, from first, we can know the 5 value because we're using a doubly linked list, right? So it's going to be very simple. So what we're going to do is first, let us try to make this particular connection, right? Let us try to make this particular, so let's try to make, let's try to make, so you have a node, right? So you want to connect, yeah, let's try to make, which connection do we want to make first? Okay, let's actually try to make this connection first. Let's see if it works, or else we will change it. Okay. So what we're going to do is we're going to add a new node, right? You have a new node. So new node dot left node will be your first node, right? Equals your first node, right? New node dot so now new node dot right node will be your first node dot right node. Simple. So you have made the connection, right? Now new node dot right node will be your first node dot right node, right? Now new node dot right node dot left node will be your new node. What does that mean? So for 5, new node is 10. 10's right node is now 5. 10's right node is now 5. 5's left node should be attached to 10, and that's what we do, right? Now, first node dot right node will be your first node, not right node will be a new node. As simple as it is, right? Perfect. Now, to evict a node, what do you have to do? You simply have to remove it from the last. So you'll have to, let's say, remove this particular node, right? This does not care about what the capacity is, any of that. That will be taken care in the LRU cache, but this has to remove this, right? So simply what you have to do is you'll have to connect this and this, right? So what you do is you simply say last node, sorry, yeah, last node dot left node. Last node's left node is this node. This node's left node is this node, right? Dot left node dot right node will become last node, right? So what do we do? So you have, I'm just taking this out, right? So you have 5, 6, and last. So you want to connect these two. So last nodes dot left will be your dot last nodes dot left is this, dot left is this, right? Now this dot right is connected to this thing, right? Now what happened is this connection is done. This particular connection is done, right? Now we'll have to make this connection, right? So we can simply say that last node dot left node equals to last node dot left node dot left node, right? Perfect. Now that that is done, what we would be doing is remove, right? Removes what is pending. Okay, so remove is also pretty simple. Uh, what we will be doing is, let us say that first we have first 2, 3, 4, 5, and last, and you have to remove 3. Okay, something is wrong with me. Okay. Now you'll have to connect these two, as simple as it is, right? So what you'll do is the node that you want to remove. So node dot left node. So node dot left node is this, right? Dot right node is node dot right node. As simple as it is, right? So node dot left node dot right node is this. Similarly, nodes right node will be this. So it will be node dot right node dot left node is node dot left node, as simple as it is. That's it. Done. You're done with our W linked list. As simple as it is. Right. Now, coming to our LRU cache. Right. This is where it gets interesting. So we will be using this. Okay. Now, what let us try to add a value. Right. Let's try to add a value. What is the first condition that you have to check? We have to check if the reference map has reached its capacity. Right. If the reference map dot size is greater than or equal to the capacity, then what we would do is we need to evict. So what we would do, we would simply call ddl dot evict. We have evicted it. Now we have to add the one. Next check. What is the next check? If the reference map contains the key, if the reference map dot contains key of key, if it contains a key, then what do we have to do? If it contains a key, then we have to make it most frequently used. Why? Because you're still accessing it. I told you that read or write, whenever you're accessing it, that will become your most recently used. So how do you make it most recently used? It's as simple, right? We already have a method for that. We can just say uh, we can use reallocate. Hmm. Yeah, I think we can use reallocate, right? That case should not be private, it'll be public. Mm, yeah, we can just reallocate. Let this be public, right? So we can just reallocate. We can say that, we can simply say that if reference map contains a key, we can simply say ddl dot reallocate of the node, right? Maybe we can return boolean to say if it got added or not. Uh, but here we'll have to create a node, right? So node uh, k comma v new node is new node of key comma value comma null comma null. It'll be null, right? Initially. Now we need to reallocate. We're gonna call new node, right? And we're simply gonna return to. Okay. Now, right? Uh, there's one mistake I made. This won't be a new node, right? Because it already contains the key, right? So I can just get the node here, and I can just get the node from the reference map here dot get of key, and I can simply use that node itself, right? Let this come at the bottom, right? Now, you have created a new node. You're gonna add it in the reference map dot put of key would be the key comma the new node, right? And right, and here after doing that, you're going to push it to the W linked list, right? ddl dot add of the new node, right? Now, uh, now one thing that we missed is that we are removing it from the W linked list, right? We are evicting it, but we're not removing that particular element from the from the hash map, right? Because hash map will still have that element, which is wrong. So instead of keeping this as void, we are going to return the particular key, right? So we are going to return the key. I'm going to add key and value here as well, right? We're going to return that key. So this it's going to be of type key, and you want to remove that node, right? So you're going to have node evicted node will be last node dot left node, right? You're simply going to return evicted node dot key, right? Now, why is this an issue? Because okay, perfect. So you're gonna return it, and here you're gonna handle it, right? Once you evict it, what you have to do is you have evicted that value, right? Now you'll have to catch it. So I'm gonna call it key equals to this eviction key. I'm gonna call it eviction key, right? And I'm simply going to say reference map dot remove of eviction key, right? Perfect. Uh, right. So this will be returned true. Perfect. Right. Now we are done with put. We're gonna go to get. Get is simple. You have the key. First, you'll have to check if the reference map contains that particular key, right? If not, your reference map dot contains key of key, right? Simply going to return no, right? Else, what you're gonna do is gonna get the node, right? So you're gonna get the node for that, right? So how do you get the node? You can just say node equals to reference map dot get of the key AR dot get of the key, right? And you get it. Node will have the value for that, but you'll have to what you have to do is you'll have to reallocate, right? So to reallocate, you'll simply call ddl dot reallocate the node. What will that do? It will remove that node. It will remove that node and it will add it, right? So you just call detailed or reallocate, and that is it, right? And here you just return. You already have a return statement. You just return the node dot value, right? Right. Okay. Okay. Perfect. So our linked list, our doubly linked list, our LRU cache, our node, it's completed, right? We have completed the implementation. Of course, you will have to test it. I'm not going to add the test cases here because it would take a lot of time, but you can go ahead and add test cases to your own implementation and try it out. Now, what we'll be focusing on is basically thread safety, right? Why is it important? Okay. Let us say that you have two, let's say that you have 1, 2, and 3, and this is the last, right? In when you deploy to production, right? Every request is a thread, right? When every thread is coming and accessing a particular element, for example, let us say that it comes and accesses 3. Now, what will happen is, let's say that thread 1 is coming and trying to access 3, right? When and let's say the capacity is 3, right? Now, when thread 2 tries to add a new value 4, right? When thread 2 is trying to add a new value 4, what is happening? Both of them are coming here, right? It's not sequential. Both of them are coming here. And due to context switching, what happens is that thread one is trying to access it. So this will become the most recently used element. But thread, new thread is going to add a value. But to add a value, you'll have to evict something because it reached the capacity, right? So thread two is actually trying to remove it, right? So one thread is trying to get it, another thread is trying to remove it, right? So what is going to happen? It might be that you can, it is probably going to say that, hey, for thread one, it's going to end up saying that three is not there, right? Or or for thread four, ideally when this is not the least recently used, right? Why? Because thread one is still trying to access it, which makes it most recently used. Then there would be another problem that the actual least recently used element is actually not evicted, right? For example, let's say 2 is the least recently used now, actually, technically, right? But this is not getting evicted, right? So these kind of problems occur, right? Because you're dealing with a multi-threaded environment. And also your hash map, right? Whenever you're trying to evict, you're trying to remove that value in the hash map as well, right? Because of all these issues, it might cause issues with hash map as well, right? Because you might actually remove something uh, from your particular W linked list, but you actually might not update it in the hash map. So hash map has that value, but your W linked list does not, right? So those issues are there. So simply what we're going to do is we're going to make it synchronized, right? We're going to make the read and write operation synchronized. Why not only write operation? Why not only put? Why not get? Because get is also doing some write operation. What is it doing? It is taking the value and it is reallocating it, right? Which is the write operation. So what we're going to do is we're going to make both of it synchronized, right? And what are we going to achieve with that? Let's see. So I'm going to make it synchronized, and I'm going to make this as well as synchronized, right? Now, what is going to happen? It's simple, right? When a function is synchronized or you're obtained a lock on a particular object, right? Now, what happens is when multiple threads come in into this particular function, what happens, right? Thread, when let's say two threads come in, one of the thread acquires a lock and it gets it, it does its operation, right? Whereas the second thread that is trying to acquire the lock will wait until it acquires a lock, right? So once the first thread has completed its operation, put or get, it is going to come out and it's going to release the lock, and then thread 2 is going to take over, right? That's what's going to happen. So with this we have eliminated this particular issue. Right? Perfect. Now with this, can you think of something which, like, what is the thing which has a disadvantages on this? Think about it. Let us say that you have 1,000 keys, right? In a production, you have 1,000 keys, right? For example, user one, user two, user 100, user 1,000. Those are the keys, right? And let's say that thread one is trying to access user one, and thread two is trying to access user 100. Both of them are not related at all, right? But still, thread two has to wait for thread one to finish its operation, then it has to do its operation, right? So if you think about it, we are what is it causing, right? It's reducing throughput, right? It's increasing the latency, right? So this causes a problem, right? So now we need to think of a solution that actually solves this problem, right? One thing that we can think of is, why don't we shard it, right? Why don't we shard it into chunks and put each of them into its own LRU cache, right? For example, let us say that you have sharded it into five different chunks, right? Each chunk will have its own LRU cache, right? So, for example, let us say that I'm going to call this sharded cache. And here, what I'm going to do is, here we're going to have the shard capacity, which will say how many chunks do you want to shard it to. And the next one is uh, the LRU cache, right? So array list, uh, let's keep it as a simple array itself. So we're gonna keep it as uh, we're gonna keep it as LRU. So this also is gonna be taking generic key value, right? Key comma value, right? So this is going to be taking again key comma value, and this is going to we're gonna call it sharded LRU, right? And this would be a sharded LRU, right? So this would be an array, right? Now, simply what we're going to do is we are going to let's create a constructor, right? Let's create a constructor, and over here, what we're going to do is that so you have the capacity, right? You have the capacity. This is going to be private. Why? Because it's internal, right? It's going to be private, and we're going to keep it final. So now what is going to happen is we need to. So you have the shard capacity, right? And you have the shard capacity, and what you're going to do is you will ideally have to create n number of or the number of LRU caches for that particular shard capacity, right? Now you have the shard capacity, which will say how many chunks you're breaking the LRU cache into. Also, each LRU cache has its own capacity, right? So we will have to pass another parameter which says int LRU capacity, right? So ideally, what you're doing is you are initializing this dot shadow LRU is new LRU cache of shadow capacity, right? And and what you're gonna do is that you're simply gonna iterate, and during each iteration you're simply going to add a LRU cache to that particular shard, right? So for shard 0 you're going to add a LRU cache, for shard 1 you're going to add a LRU cache. Okay, so LRU cache, oh sorry, shared LRU cache of I equals to new LRU cache of capacity, which is LRU capacity, right? As simple as that. Now we have a shard, right? Now you might ask me, Siddharth, how do you know which shard has a particular key? Simple. It's the same concept from consistent hashing, right? So what you're going to do is you're going to take the key, you're going to mod it with the number of shards that you have, and based on that, you're going to go to that key. Right? As simple as that. So, so what we're going to do is let's create a function which will tell us what shard, right? Let me call it which shard, and this will ideally tell us which shard the key is in, right? So let us say that you have key, right? And here, what you're going to do is this is going to return which shard it is, right? So which LRU cache it is, which shard, right? So here, what we're going to do is we're simply going to hash the key, mod it by the number of shards that we have, and then we're simply going to return that particular shard, right? So we can just simply say LRU cache of cache, uh, we can call it sharded cache equals to, uh, we need to mod it, right? So what we're going to do is we're going to take the hash, right? So for simplicity, I'm just going to take a simple hash function, right? Uh, mod this dot shard capacity, right? So this will give you the n number of shards. So simply you're going to return So this will give you the this will give you which particular index it is in, right? Actually, this will give you which particular index it is in, right? It'll give you the number. So int index will give you the number of which shard it is in. Because capacity, let's say 5, capacity is 5. You're modding the key, you're hashing the key and you're modding it. It'll give you the shard, which shard index the LRU cache is present in, right? And what we're going to simply do is we're going to take the sharded LRU and return the index of it. So this particular this value would contain the LRU cache for that particular shard, right? So whatever get operation, right? Whatever get operation you have, get of key, you can simply call the with shard function of the key, and you'll get which shard it is actually, right? So you'll know which shard actually it is. So you can just copy this shard, and you can simply return the uh, shard dot get, right? This will return the value, right? And similarly for public void put, or I believe this is boolean. Let me just keep it void for simplicity. Void put, when you want to put a particular key and a value, right? So you want to put a key and a value, right? So you have a key and a value, right? So what you're going to do is the same thing, right? Which shard of the key, right? So you're assigning a particular shard, right? You're hashing it, you're modding it, you get a particular value, and you'll be returning that particular shard where you can add the data, right? And you'll simply return same thing, shard dot put of key comma value. As simple as it is, right? Oh, sorry, start, right? As simple as it is. So what does this achieve? This makes sure that the each shard contains only certain number of uh, LRU cache, and for that each LRU cache we made a thread safe, right? But what is the trade-off? The trade-off is that it's straightforward. It's just that for you for in a production environment you have to divide the shards. You have to divide the LRU cache into multiple shards, right? Which is the trade-off. You don't have a global shard. Sorry, you don't have a global LRU cache. You have you have shard-specific LRU cache, and each LRU cache has its own hash map, doubly linked list, and nodes, right? So there's a trade-off. So if you look at concurrent hash map in production, ideally inside it does something similar to this, right? So with this, we have achieved thread safety, and we have made sure that you know uh, for a large amount of keys, right? We are sharding it, we're breaking it into chunks so that a particular shard can handle only certain number of keys, right? Certain number of capacity. So yeah, I think with that being said, we are done with this design. I will upload the GitHub link in the description. You can go through the code and you can try to understand what's happening. So this is how your systems are built, right? By solving just leak code problems, you don't know where it's actually being used. For example, we used W linked list over here. We used LRU caches over here. We used hash maps over here, right? So these things we have used it in individual lead code problems or any algorithmic problems, but we don't know where it's actually applied it, right? For this exact reason, I've created a platform. In this particular platform, you can solve such questions which uses all these concepts to build real systems, right? It's called as uncommon.org. I will attach this link in the description as well. You can check out this, and you have a lot of problems which will actually replicate how you would do it in your real-time job, right? Most of the people know how to solve these equations, right? But they don't know if they can engineer a system, if they can build a feature in an unfamiliar code base, or if they can navigate an unfamiliar code base, right? This is exactly the reason I've built this particular platform. And you can go through a lot of problems which actually, uh, you know, uh, gets you prepared for building in a real life system, right? And you can check it out. You can solve problems over here. And I believe most of the companies are switching from traditional lead code style to these kind of questions where you are given a repo and you're supposed to build a feature on that, right? So you can exactly practice all these concepts here. And I will keep uploading more questions and bring out a lot of more features which I have in mind. So yeah, just sign up and check it out. Okay? Well, thank you.